Okay, let us continue our study of DFA state minimization. I just start with a recollection of the mathematical result that we have proved. So we start with a DFA Q sigma delta S F, and we have defined an equivalence relation on Q as two states P and Q are called equivalent if and only if for all x in sigma star, if I apply delta repeatedly starting from Q, this is a final state if and only if delta hat of Qx is in the set of final states. And we have proved that this gives us the so-called quotient construction. That is, we have defined a machine D prime, which is also denoted as Q prime, same in full alphabet, delta prime, S prime, F prime. So we have taken Q prime as the set of all equivalence classes of Q under this equivalence relation. So we have collapsed each individual equivalence class to a single state. Sigma remains the same. Start state we have defined as equivalence class of the start state. Set of final states we have defined to be the equivalence classes of final states in the original machine, and delta prime on an equivalence class P for an input symbol A is defined as the equivalence class of delta PA, and we have seen that this can be done in a safe and consistent manner. Okay, and we have also seen that no further state collapse is possible on this D prime, the quotient structure. Okay, now we would like to ask this question algorithmically. So we want to find an algorithm to compute D prime from D. Okay, so this algorithm and some associated issues we will discuss in today's class. We will essentially build a two-dimensional table to the table. Okay. So although we say this is P and Q, PQ equivalent by symmetry, Q is also equivalent to P. So for each pair P and Q, which are equivalent to one another, we'll use this symbol. Okay. So this is not exactly, this is not an ordered pair, this is an unordered pair. So P is equivalent to Q and Q is equivalent to P. This is written this. Also P is not equivalent to Q, Q is not equivalent to P. Then also we will denote this. So this two-dimensional table indexed by the states. And because of the symmetry, it's basically I would say, a triangular table. We do not need the entire Q cross Q thing. Okay. So I will store for the pqth element, this table will store some symbol called unmarked. If P can be equivalent to Q and marked if P is known to be not equivalent to Q. Okay, so maybe I write it this way. So eventually I will build up a table whose pqth entry is the same as the qpth entry. This will be unmarked. Okay, if P is equivalent to Q, and the pqth entry will be marked if we know that P and Q are not equivalent. So I will use some symbols for this marking. Maybe I will use minus. This is the unmarked symbol. For marking, I may use symbols like marked or marked, something like that. Okay. So this table is built using the following algorithm. Okay. So first start with all entries unmarked. Initially, we keep the possibility that everything can be collapsed to a single state. So maybe I just give it the numbering. So this. Okay. So this is the beginning stage. Then I will do some kind of initialization. Recall that if P is a final state and Q is not a final state, or conversely, P is not a final state and Q is a final state, then they cannot be equivalent by definition, because upon epsilon, this condition is not satisfied, right? For x equal to epsilon, this condition is not satisfied. So they cannot be equivalent. So to start with, I will mark the pair, unordered pair PQ. If P is a final state and Q is not a final state, or P is not a final state and Q is a final state. So this is kind of initialization. With this we will start. Okay. Then we will enter a loop. Okay, we try to identify a pair, unordered pair, P comma Q, and some symbol A, such that delta PA and delta QA, this pair, unordered pair actually, is marked. Okay. If such a combination of states PQ and a symbol A in the input alphabet is found, then you mark the pair delta PA, delta QA. Repeat this loop until no further or no new marking is possible. And then the loop breaks. Finally, if you declare two states P and Q as equivalent, if and only if this unordered pair PQ is unmarked. Okay, so this is the straightforward algorithm. We will look at its performance a little later. Okay, so you start with pairs PQ and mark them. Okay, so initially everything is unmarked. So it is even in the worst case, every state or all the states can be merged to a single state. This is very much possible. So until we discover a reason why we can say two states as non-equivalent, we will not mark them. Okay. So in the initialization phase, we have reason. We see that a state P is in final state, set of final states, and another state Q is not in the set of final states. Then definitely they cannot be equivalent, and we have a reason to mark P comma Q, this unordered thing. Or conversely, if P is not a final state, Q is a final state, they cannot be equivalent, so we mark them. Next, inside a loop, so long as we can find this combination of states P, Q and input symbol A, okay, such that we have already marked delta PA and delta QA, where delta is the transition function of the given DFA, we mark this new pair delta PA and delta QA and keep on doing this until eventually we run out of choices for P, Q and A. And when this loop terminates, you simply declare two states P and Q as as equivalent if and only if that unordered pair P comma Q is not marked, is left unmarked in the table. Okay, so we'll look at the running time and all this stuff from a little later, and also the fact that this actually computes this equivalence relation correctly. But before doing that, let us look at a few examples how this algorithm works. So here is one. So on this top you will see a DFA. Whatever language it accepts, this is not very important. So you can actually write a regular expression for the language it accepts or it rejects, whatever. So this is the start state, which is also a final state. And so I am not looking at whatever is happening below. I will come to that little later. Okay. So I have marked these states. I have named this state as A, B, C, D, E, F, G, H. And this is the transition diagram. Okay. Whatever it does, it's not important. This is the transition diagram, and this is the so-called transition table. A upon input 0 goes to C. So A upon input 0 goes to C. A upon input 1 goes to D. A upon input 1 goes to D. F upon input 0 goes to G. F upon input 0 goes to G. F upon input 1 goes to H. F upon input 1 goes to H. Okay. Okay. So, okay, so I will build a two-dimensional table. It is to be read this way. Okay. So initially, okay, so it's a two-dimensional table that store a total of n choose 2 entries. N choose 2 because there are two element subsets of the set. N choose 2. N is the number of states. Okay. So here 1, 2, 3, 4, 5, 6, 7, 8. Is it so? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So 8 choose 2 entries are there. Okay. So how do I read it? So let's consider C, G. So I start from C here, G here. Okay. So this is the thing. C, G. So this element I will call marked or unmarked. Okay. Cross means marked, minus means unmarked. Likewise, if I look at BE, so this is B. Sorry, this is B. This is E, so it is unmarked. Okay. So this, I would say, configuration of the table, this is after initialization. It is this table. Okay. So initially everything is unmarked, minus, 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 minus. Then I mark final, non-final pairs. So A is a final state. So I will not mark A with G or A with H, but I will mark A with B, C, D, E, and F. So A with B, A with C, A with D, A with E, and A with F. Okay, because A is a final state, B, C, D, E, F are not final state. So I will initially mark this A through A, B through F. G and H are also final states, so I will not mark them. Okay. Now if I look at B, it is a non-final state. And the question of marking it with A is already considered, so I will move forward. So B with C, D, E, and F, they are all non-final state, so I will not mark them. C, D, E, and F. Okay. Whereas G and H are final states, so I can mark the pair BG and BH. So BG, BH. So the same is true for C, D, E, and F. This unmarked, whereas GH, 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 F also GH. Finally, look at G. Okay. So of course it is not marked with so the pair G, E, G, C, G, B, this will not be marked, but I have already considered this unordered pair when I considered B, C, D, E, F, and so on. G is a final state, H is also a final state. Therefore, I will not mark the pair GH. So this is left unmarked. Okay. So now I will start my loop and one by one look at this, in some order, okay, to see whether I can mark these new pairs, okay. So this second part of the table says all the things that I can mark at the end of step 3. Step 3. So this is end of step 2. And this is at the end of step 3. Okay. Now let us see one thing. So this quantity A, G, and I want to mark it. Okay. So you start from A. Okay. Okay. So let's look at this. Maybe this one. So this corresponds to A and G. And you see that delta A. So I need some space to write anyway. Maybe I write it here. Delta A upon 0. What will be this? Delta A0 is C. And if I look at delta G0, what will be that? Delta G0 will be H. Now let us look at the pair CH. Is it already marked? So you come here C, come here H, it is already marked. So I can mark this. Okay. So let us look at another example. Which one is good, I do not know. Or maybe I use a new color, red. So let us look at maybe CE. Is it good? Maybe C is not that good. I have also marked B, E. Okay, actually this example is a little bit too easy. Anyway, it doesn't matter. So maybe let us look at B, anything, B, D maybe. Yes, B, D maybe. No, sorry. Okay, any example you choose. This is actually an easy exercise. Anyway, so let us look at this. Let us say CE. CE. Okay. CE. And then let us see what happens. C and E. Okay. Let us look at delta C. Delta C. 0 is B. And delta E0. Delta E0 is G. And then I look at whether B comma G, this thing is marked. So B, G. Okay, so this is marked. And therefore C, E is marked. Okay. So this is how this table is prepared. In fact, you can see that in a single iteration, if I look at this, I can introduce these new marks. 1, 2, 3, 4, 5, 6, 7, 8 new marks. On the other hand, if I look at something like BD, so maybe let me use yet another color. Maybe which one? Yeah, maybe this. Let us look at this. Okay, BD. So B and D. So let us look at delta B0, delta D0. What is delta B0? It is C. What is delta D0? It is D. Okay. Also let us look at delta B1 and delta D1. Okay, so what is delta B1? This is E. Delta D1, this is F. Okay, so now let us see whether this pair C comma D is marked. Here I can see CD is not marked. What about EF? EF is not marked. So at this point, CD, this is not marked. EF, this is also not marked. So I cannot mark this. It will keep like this. Okay. And you will see that this is the final state. I can no longer mark this pairs BD, CD, BC, EF and GH. Okay. So that essentially stops the procedure. Okay. So now what does it say? Simple thing is GH pair is not marked. So G and H are equivalent. Here you see EF. This pair is not marked. So this says that, okay, maybe I use yet another color. I do not know which color is available now. Maybe white or okay, let me use white. Okay, so this says at the end of the algorithm is G is equivalent to H. This says that E is equivalent to F. This says B is equivalent to C. This says B is equivalent to D. This says C is equivalent to D. So these three things together say that B is equivalent to C is equivalent to D. So the idea is that I can now club together these three states B, C, D. Okay, so I can also club together E and F. I can also club together G and H. So if I do so, this DFA results. So G and H are clubbed together. E and F are clubbed together. And here you see B, C, D, they are all equivalent to one another. So I have clubbed together. And A is definitely not equivalent to any other thing. So it will stay. Okay. And you see that C and B, C and D are all equivalent. So all this thing will come to a single equivalence class, which is this. And A itself is an equivalence class. So 0 goes here, 1 it goes here. It doesn't matter whether it is 0 or 1. It's its equivalence class of B, C, D. Okay. Here also you see, start from the BCD equivalence class. If you read 0, you will go to B. If you read 0, you will go to D. So in other words, you will stay in the equivalence class BCD. So that justifies this loop. Okay. On the other hand, if you read 1, okay, from B you go to E, from C you go to E, and from D you go to F. Okay. But this does not matter because E and F belong to the same equivalence class. So this one, E comma F. And then also you see that 0, 1 here, 1, 0 here. So it will end up in the, starting from EF, you will end up in the equivalence class of G and H, irrespective of whether it is 0 or 1. And here actually, 1 you stay here, 0 you come here, 0, 1 you stay here. So for each of 0 and 1, this is a loop. Okay. So this is a procedure And this is a simple one, but it still illustrates how this algorithm works. More importantly, this also illustrates how this equivalence definition works. Okay, this is an explicit example. Of course, we have seen a bigger example in the last lecture. And this is also a confirmation that these transitions among equivalence classes are safe enough. Of course, we have formally and mathematically proved this, but this is also a confirmation and illustration. And also, this DFA is a minimal DFA in the sense that this cannot be collapsed further. Okay. Good. Now, I will give you yet another example to illustrate that. This loop may run for multiple iterations. Okay. So let us look at this. Here sigma is just 0. And this DFA says it accepts all strings W over this unary alphabet such that the length of W, or for that matter W, or maybe I write it this way, a power n such that n is congruent to 3 modulo 8 or 3, 4, 5, 6, 7. N is congruent to 7 modulo 8. This is what this DFA over the unary alphabet accepts. Okay. And then D and H are the only accept states. Non-accept states are A, B, C, E, F, G. Okay. So this is after initialization, that is step 2. Okay. So A, I will mark the pair AD and AH only. Okay. So AD, AH, B also BD and BH, B, BD, BH, C, CD, CH. This is because A, B, C are non-accept state. D I will mark with E, F, G. Okay. D I will mark with E, F, G. Okay. E I will mark with H. E with H, F with H, G with H. So this is the initialization marking pattern. Of course, I have used 0 here to indicate that these cells are marked during the initialization stage. Okay. Then I go to this loop. Okay. Maybe I will look at this, this, and try to mark this, try to mark this, try to mark this, try to mark this, try to mark this sequence. Okay. So let us see what happens if that is the first iteration. A, B. Can I mark? Upon 0, A goes to B, B goes to C, B, C. B, C is not marked. So in this iteration, I cannot mark this. Okay. So this is iteration number 1. Now if I look whether I can mark B, C, upon reading one symbol, B goes to C, C goes to D. Okay, so B, C becomes CD after reading 0. And we see that CD is marked. This is marked during initialization. So I mark this. Okay. So likewise I can mark this. Okay. So this is kind of shifting this direction by 1. So this one I cannot mark because of this. This one I cannot mark because of this, but I cannot mark this because of this, but this I can mark because this is already marked. This I can mark because this is marked, and so on. Okay, so you can see after first iteration of the loop, if I keep on marking this direction, this, I can mark only these cells. Okay, this. Here I have used 1 in order to indicate that this is marking the first iteration of the loop in step 3. Then I look at this. Can I mark this? Now I see that A, B. So this is pair A, B. So upon input of the next symbol, A goes to B, B goes to C. And I can see that BC is now marked. Initially, after initialization, BC was not marked. But in stage 1, this is marked. So I mark this. Okay. Similarly, you can find out, I can mark this because of this one. Okay. I can mark this because of this one, and so on. So only these 4 markings are possible. And then you can see that you cannot mark this, and this. So that is the end of the procedure. But this 2 indicates that I have marked in the second iteration of the loop in step 3. Okay, 0 means initialization, first iteration, 2 means second iteration. And this example illustrates that this loop can run for multiple iterations. Anyway, by making this loop larger, okay, so you can effectively make as many iterations as you want. Anyway, that's not important. The only thing is that this may, unlike this previous example where everything finishes in a single iteration, you may have to make multiple iterations. Okay. And what remains? It says that A, E become equivalent because of this. B, F become equivalent because of this. C, G become equivalent because of this. And finally, D and H become equivalent. So AE, BF, CG and DH. And now if you write this delta prime, it will look like this. And this says that this is going to accept all a power n such that n is congruent to 0, 1, 2, 3 modulo 4. But that's quite obvious, right? An integer is congruent to 3 modulo 4 if and only if it is congruent to either 3 or 7 modulo 8. Okay, so that's the algorithm and a couple of examples that illustrate the working of the algorithm. Let me now ask the question. What is the running time? Then we will look at the correctness of this algorithm. Okay. So first of all, how many pairs are involved? Number of unordered pairs. Of the form PQ is nothing but n choose 2, where n is nothing but the size of Q, that is the number of states. Okay. So initially you mark certain things. Anyway, what you can see that step 2, or even I may start with step 1, where you unmark everything. Okay, initialize. This is a pre-initialization step. This can be done in theta n square time. And step 2, which is actual initialization, that is marking final and non-final pairs. This can also be done in theta n square time. And step 3, in each iteration you mark at least one unmarked thing, and this is the total number of Okay, pairs. Okay, so this is again, I can say this is polynomial in n, and not a very high degree polynomial, because this is the number of unordered pairs p comma q. Okay, so in fact you can see that if you build a list of unordered pairs and one by one you try to do this, anyway, whatever, n square, n cube, something like that, it's not too inefficient. And step 4, which means you eventually identify. So once again you have to take a look at all the elements of that table. So this can also be done in big O of n squared time. Okay, big O or big theta, whatever. Okay, so this is an efficient minimization procedure, efficient algorithm. And given any DFA, we can therefore minimize by using the quotient construction using this algorithm. So provided that the algorithm works correctly. So this is a proof which I would like to present now. So now first I claim that this algorithm works correctly. So what does it mean formally? So that essentially is equivalent to saying that the pair, the algorithm marks some unordered pair P and Q if and only if P is not equivalent to Q with respect to that equivalence relation. Okay, so eventually if some pair is not marked, I call them as equivalent. So if P and Q are not equivalent, the idea is that at some stage of the algorithm this is marked. Okay, so let us prove this formally. First maybe this. Okay, so here I proceed by induction on number of stages of step 3. Okay, so if this is 0 basis, that is before starting step 3 itself, P and Q are unmarked. That is possible when P is in F and Q is not in F. So this is one possibility, or just the opposite. P is not in F whereas Q is in F. But then by definition of this equivalence relation, it follows that in this case P cannot be congruent to or equivalent to Q. So on the other hand, inductive step. Okay, so suppose that the algorithm marks PQ at some stage. Okay, so the algo marks PQ at a later stage. What does it imply? It implies that it must have found some symbol A in the alphabet such that delta PA, delta QA are marked or is marked. Pair is marked. Okay. For some A. That is the reason in this iteration the algorithm marks P and Q. So by induction, okay, the number of stages, it follows that this is not congruent, okay, not equivalent. But if P and Q are equivalent, okay, and then if I apply A, we have proved in the last class that then delta PA and delta QA are also equivalent. Okay, so P, this implies this we have proved in the last class, and in fact this is very necessary for the definition of delta prime to make sense. So this in turn will imply the contraposition of this. If they are not equivalent, then P is not congruent to or equivalent to Q. Okay, marked for some iteration. So this is by induction, by inductive hypothesis. We have this, and therefore from the definition of delta prime, it follows that P is also not congruent to or equivalent to Q. Okay, so this direction of the proof is fairly straightforward. The converse is actually also straightforward. We will show that if P is not equivalent to Q with respect to that equivalence relation, then the algorithm will mark the pair PQ at some stage. Okay, so for the converse, I will prove this. So I assume that P is not equivalent to Q to show that the algorithm marks the pair P comma Q at some stage or step. Okay. So how do we proceed? Since P is not equivalent to Q, this implies there exists some X in sigma star by definition of this congruence or equivalence relation, such that delta hat of Px is in F and delta hat Qx is not in F. Either this or just the opposite. Okay, so this is not in F, this is in F. Okay, this is another possibility. So this hypothesis implies this by definition of the equivalence relation delta, this equivalence relation. Okay, so now we proceed by induction on the length of X. Okay, so basis, if this is 0, this says that if this is epsilon, this basically says that P is in F and Q is not in F, or conversely. Okay, but then the algorithm marks the pair PQ in step 2, initialization step. Okay, so then suppose that X is, so induction basis holds. Next, suppose that this is greater than or equal to 1, and you write X as AY. Okay, then what does it follow from this? It is given that so what is delta hat of Px? This is nothing but delta hat of Pay, which is nothing but delta hat of delta PA y. So this now says that for this y we have delta hat delta PA y is in F, and delta hat of delta QA y is not in F, or the converse of this. That is, this is not in F, this is in F. Okay, but the size of y is 1 smaller than the size of x, that is length of x. So by induction, the algorithm marks this pair, this and this. Okay, so by induction, this pair delta PA is marked at some early iteration, but now we have some P and Q, and we see that delta P and delta QA, this combination is marked. So now this algorithm will mark P and Q. Okay, so that's essentially the proof. Okay, fine. So that's about this algorithm, its correctness and necessary things. Okay, so that is fine. So now I will just stop with a little bit plan for the future. So essentially the quotient construction. Okay, so to sum up, what do we do? How to obtain the a minimal DFA? The first thing is throw away all. Okay, unreachable states. I have already talked about this. And then do the quotient construction to collapse equivalent states. And this essentially gives us with a DFA where there are no unreachable states and all states are mutually non-equivalent. So we cannot safely collapse them together. Okay. So this is basically a DFA, a DFS or BFS, and this can be done by the algo covered today. So next we ask the question, suppose for a given L, okay, somebody builds a machine, let us call it M. Somebody builds a machine called M such that this is same as this and this. Then what we do, we apply the quotient construction with respect to the equivalence relation on M, and we get a machine M prime. Then we also do the same thing on N, and we get a machine N prime. Okay, so this is the quotient construction. And the question is, what is the relation between M prime and N prime? Okay. So if a machine, okay, so you also assume that M and N have no unreachable states. So first throw away all the unreachable states and then do these quotient constructions such that you have no equivalent, no collapsible states also, no collapsible pairs of states also. Okay. So what is the relation between M prime and N prime? So we will now see from in the next two classes that M prime and N prime are essentially the same machine. What is meant by same? So if we just name the states of M prime in a suitable manner by using the names of the states of N prime, this will exactly be the same machine. Okay, M prime and N prime will be the same machine. So that means this minimum or minimal DFA whatever way you construct is a property of L, the language. Okay, so it is not a property of the individual machine M or individual machine N. Okay, because eventually I can reduce everything to a machine M prime or N prime or P prime, Q prime, whatever machines you design. Eventually you will, after this minimization, you will get the same machine, same minimal machine, and therefore the same minimal DFA is a property of the language with which we started, not of the machine that we generated in the intermediate steps of our construction. Okay, this requires quite a few interesting and non-trivial results. We will look at this in the next two lectures. Okay, so until then, goodbye.